Нет.
Нет? Ну ладно. Знаешь? Вот.
Вот, все встанет, начнем писать.
Ну хорошо, я так расскажу словами. Нравится, в каком языке говорить. Значит так, сегодня мы закончим с простыми корнями русского появления, а потом мы вкратце без доказательств поговорим про алгебры Ли. Значит, во-первых, что такое неразложимая система корней? Здравствуйте. Так, пока по руке, если будет Аналия, то мы перейдем на английский. Значит так, мы хотим доказать, что система корней неразложима, тогда и только тогда, когда система простых корней не разваливается в два ортогональных подмножества. Вот. Нет, что не приводимо, извините. Сейчас, я говорю, что фи неприводимо. Тогда, когда нельзя представить для объединения фи это фи1 объединить фи2. С условием, что линейные оболочки фи1 ортогональны фи2. То есть пока у нас была только одна приводимая система корней, это было А1 на А1. Но понятно, что можно взять любые две системы корней, поселить их в два ортогональных пространства, и тогда они будут именно что ортогональными.
Что другие неприводимые, типа, очевидно.
Нет, конечно же, это не очевидно. Свойство такое. Назовем его теорема. Фи неприводимо тогда и только тогда, когда дельту, ну то есть систему простых корней какую-то, нельзя разбить в виде дельта 1, дельта 2. Так что любой элемент дельта 1 ортогонален любому элементу дельта 2.
Что дельта?
Система простых корней.
Для любой системы простых
Как бы
корней.
без разницы, сейчас давайте скажем. Значит, что мы знаем? Мы знаем, что все системы простых корней сопряжены под действием группы Вейля. Действие группы Вейля состоит из ортогональных преобразований. Поэтому, если одну систему простых корней можно разбить, то все другие тоже можно. Если эту нельзя, то и остальные тоже нельзя. Yes. Yeah. So at the moment we just follow Humphreys and we finish studying simple roots. It's just written if the root system can be decomposed into two orthogonal subsets, then we will prove it right now that the base can be decomposed into two orthogonal subsets.
In space that means decomposing.
Irreducible. So if you ask for the terminology follows the book. If the terminology is used, then it can be taken as the standard one. Okay. In this theorem, it doesn't matter which base do I take, because every two deltas are can relate one into another direction of the wave group, and if one can be decomposed in such a union, then any other also can be decomposed. Now let us prove this theorem in two directions. First of all, if phi is 1 and 2, this means that each vector from the first part is orthogonal to each alpha 2 from phi 2. Okay? In this case, take any base delta, and it splits. Delta 1 is delta with Q1, delta 2 is delta with V2. And these two subsets are any two elements orthogonal. In one direction it goes. Now we want the other direction. If for some base delta equals delta 1 union with delta 2. So what do we know? So we know that they are orthogonal. In this case, the reflections commute. If alpha 1 equals alpha 2, then sigma alpha 1 sigma alpha 2 equals sigma alpha 2 sigma alpha 1. Okay? It is just geometry. If this is alpha 1, this is alpha 2. What is sigma alpha 1? Sigma alpha 2. This is the central symmetry. And in the other direction, it is the same central symmetry. And this picture proves in any dimension. Since the mirrors of these two reflections, their intersection is a subset of dimension n-2. And so the essential part of this composition, it happens in a two-dimensional space. Is it clear? Okay, so I know that any two sigmas commute if we take alphas from orthogonal subsets. And what now? I want to prove that phi will be also decomposable. So how do I prove it? I know that take any alpha from our phi. What did we prove at the previous lecture? We proved that any root is conjugate to a root from a base. Not conjugate, it is exists some element of the wave group and such that W alpha belongs to a base. Okay? We can move it to a base by an element of a wave group. But now, suppose that it belongs to some, so we split the delta. We split the delta into two parts. If W alpha is in some, for example, if it is in delta 1, then in this element, we prove that the wave group is generated by simple reflections. So some reflections are from delta 1 and some from delta 2. So there are sigma alpha I taken either from here or from here, and they commute. So in this case, I can write W alpha equals W2, W1 alpha in such a way that all simple roots are from the second part, and here all the simple roots, so simple reflections, from the first part. Is it clear? So there were two types of reflections. Reflections with respect to the first half and to the mirrors from orthogonal to the simple roots from the first half and to the second half. And they commute. So I group them. First I do all this stuff and then all the orthogonal vectors. What happens now? So I suppose that alpha from no, I didn't want this. I wanted to say if this is in delta 1, I want to say that what is now alpha? Maybe another direction would be better. Alpha is omega W1 minus 1, W2 minus 1. I'm sorry, I will say that this will be 1 and this will be 2. And here 2 and 1. Try to some So the idea is that this vector was from delta 1. First I want to apply something from delta 1 and then from delta 2. No, delta 2 and delta 1. Sorry. Oh. Just what do I want to do? I want here to apply first, so this is my element. This is my element which is from delta 1.
W. This is W. In brackets.
Yes, it is WF. It belongs to delta 1 by my assumption. I want this and then this. Now I should one here and 2 here. 1 here and 2 here. And 2 here. So what happens now? This is from delta 1. These are simple reflections with respect to alpha 1. If you remember the formulas, each simple reflection subtracts some alpha from delta 1. This is a sequence of simple reflections, sigma alpha I, where alpha I from the first half. Okay? So if you remember the formula, so we subtract alpha I from delta I with some coefficients. What was our formula? Sigma alpha applied to x was x minus 2 x alpha alpha. It was our formula from the geometry course for the reflection sigma alpha. So now we've had some vector from delta 1 and we subtracted some vectors from delta 1. This is a sum of elements, sum of simple roots from delta 1 with some coefficients. Okay, but this was now this was the chain of simple reflections with respect to vectors orthogonal to all this stuff. So it doesn't act. So we can just forget this and obtain that alpha is in a span of delta 1. So if the wave group sends alpha to delta 1, then alpha itself was in span delta 1. Is it clear? No. So it equals this sum. Yes, the action of W2 is trivial because all these vectors are orthogonal to all these vectors. This is the chain of simple reflections with respect to vectors from the second orthogonal component.
смысле, оставляет в той же плоскости?
Вообще ничего. Okay, once more. What did we have at the previous page? Of some A1 alpha 1 1 plus A2 alpha 1 2 etc. These are some coefficients. They can be negative, can be zero. Okay. And now what is W2 minus 1? It is the change sigma alpha to 1, sigma alpha to 2, etc. Sigma alpha to j. But each alpha to k orthogonal to alpha 1l. Okay? What does it mean? Sigma alpha to k applied to this vector. It is alpha 1l minus 2 scalar product here. Alpha 1l scalar product with alpha 2k. But so this is 0. So this sigma equals alpha 1l.
Что-то у меня в голове сломалось. Отражение относительно ортогонального вектора,
Оно сохраняет всю ортогональную плоскость, оно сохраняет.
но оно же вот именно вектор меняет сам по себе.
Подождите. Давайте я по-английски скажу. Или по-русски. Смотрите, вот у вас есть плоскость.
Да.
А вот есть...
Вектор.
это у нас будет это карандаш, это сигма, это будет альфа 2К.
Да.
Вот эта вся плоскость, она неподвижна.
Да.
Поточечно неподвижна. И вот вся ваша картинка, вся вот эта вот длинная скобка, она лежит в этой плоскости. Ну вот видите, вот это отражение, а плоскости на месте. Вот вектор поменялся, а плоскость осталась на месте. Это плоскость отражения. Вот это альфа 2К. Это плоскость отражения вектора, который ортогональный. Каждый вектор в этой плоскости никуда не девается. Он просто на месте. Вы сделали сигма 2К. Вот как бы. Один вектор поменялся, остальные на месте. Идея в том, что вся вот эта скобка, она сидит в том, что на месте. Вот здесь она сидит. И она так сидит для всех сигмочек отсюда. So this is true for all the sigmas from this decomposition. So it doesn't change this vector. So what was our aim? We said, suppose that delta can be decomposed into two orthogonal subsystems. Then our root system can be decomposed into two orthogonal subsets. So let me explain this. If by the action of the wave group of alpha belongs to delta 1, say that alpha belongs to phi1. So phi1 will be the set of vectors from the W orbits of the elements of delta 1. So phi1 is the union of W orbits of elements of delta 1. Okay, and with this this part shows that phi1 leads span of delta 1. On the other hand, we can define phi 2, and we know that phi is the union of phi 1 and phi 2. Because each vector, by the action of our Veil group, can be moved to a simple vector, to a simple root. Okay? So it is either in phi 1 or in phi 2. And now phi 1 lives in span delta 1, it lives in span delta 2. So phi 1 is orthogonal to phi 2. Is it more or less clear? Okay, maybe then I prove two corollaries of this theorem. Wait a moment, the theorem. Let us prove two corollaries and then I'll check the time. Corollary 1 is that first that phi is reducible, then with respect to the ordering which we've had before, the dominant order. So if the difference is a sum of positive roots with positive coefficients with respect to this ordering, there is a unique maximal root beta. And if we decompose beta into simple roots, then all k alpha are positive. So do you know what is a representation with the highest weight? Слышали когда-нибудь про представление со старшим весом?
Да.
Да, замечательно.
А оно и всегда бывает же, да?
Кого угодно это бывает, сейчас скажу. So, at this moment, if you take the corresponding Lie algebra, so if you know something about this, it is the corresponding Lie algebra, and it acts on itself by the commutator. Then this this maximal, so then the set of weights of these representations will be exactly the root system, and this beta will be the highest weight of the adjoint representation. This is if you have studied it in the algebra course. Just to explain why I'm proving this corollary about the maximal root.
Can you repeat it?
have some time, I will talk today about how a root system, how an irreducible root system corresponds to a Lie algebra. But if you have a semi-simple Lie algebra G, what is its simplest representation? You always have your adjoint representation. So your adjoint representation is that any element of G is a linear operator which comes here and commutes with all the other elements of your Lie algebra. So is it a representation with the highest weight? So the answer is yes, definitely it is. So the set of weights of this representation is exactly 5, and the highest with respect to this dominance order is exactly the maximal root of your root system. We should have some examples. So do you know SL2 example? Maybe first I prove the corollary, and at the end, or maybe at the seminar, you just say that I promised you to tell about SL2. Okay. Let us prove this lemma. So, first of all, what do we know from the previous lectures? So delta is fixed, definitely. When we talk about the highest or about the maximal, delta is fixed. So we have a finite number of rows, so phi is finite. And half of them are positive, so we take in all the vectors from phi plus. And so we have a finite number of betas of this kind. All the coefficients are integer. So clearly there is only a finite number of possibilities for maximal elements. So each beta expands as this sum with K alpha from this. So there is at least one maximal element with respect to is it obvious? Just because if it's not maximal, it can be made greater, and this chain cannot last infinitely because the sum of K alpha is bounded. Okay. Now we want to prove that it is unique, and we want to prove this. How can we prove first this? A little bit of playing with angles as before. If some K alpha are 0, if beta is maximal, but some of K alpha are 0, let delta 1 with those alphas, k alpha is strictly positive, and delta 2 with those alpha such that k alpha in the decomposition of our beta they are 0. But what can we say now? So alpha, take alpha from delta 2 and take our beta. Then it is not positive. It is not positive because otherwise we could increase our beta.
What?
We said that if we have two roots such that this angle is acute, yeah, exactly, not acute, obtuse. Just one moment. One moment. It should yes, it was so we know that all the angles between the simple roots they are obtuse. Да, тупые. So they can be acute. So beta can be decomposed like this in this way. And if we just expand this scalar product of a simple root and a positive sum of simple roots, all the sums will be non-positive. Once more, if we expand this stuff, this will be the sum of k maybe I write prime here. Sum of k alpha, alpha prime alpha. Okay? These are products, scalar products of two simple roots. Alpha prime is fixed and alpha is any vector from our base. Okay? Once more. For the simple roots, all the angles are obtuse. So this is non-positive. Yes. So we suppose that now that phi is irreducible. So it cannot happen that all delta 2 is orthogonal to delta 1. So there exists alpha 2 prime from delta 2 such that alpha prime is not orthogonal to delta 1. Okay, and so the scalar product of alpha prime and beta, it will be strictly negative since in this decomposition the corresponding k alpha will be also non-zero. I can repeat.
Why does it exist alpha 2 primes? Delta 2?
We assume that our system is irreducible. So its delta cannot be splitted. Не может система простых корней не может развалить два ортогональных подмножества. So it cannot be decomposed at delta 1 and delta 2 with delta 1 orthogonal to delta 2. So if we take delta 2, there is at least one vector which is not orthogonal to some vector. So there exists alpha 1, 0 such that alpha prime with alpha 1, 0 is non-zero. It is strictly negative since they are both simple roots. Okay. So in this decomposition, we will have k alpha 1, 0. It is not 0. And we will have alpha prime, alpha 1, 0. This will be strictly negative. It is not 0. It is positive. So k alpha is a coefficient in this decomposition. It is not 0 because this was from the delta 1. They are assumed to be non-zero, so positive. And this is strictly negative, so this summand is strictly negative, and all the other summands are non-positive. If we express this stuff, one summand is negative and all the others are not positive. This is negative. What next? But now we know that alpha prime plus beta is a root. Do you remember that lemma? If we have an obtuse angle, then the sum is also a root. It was many lectures ago. So that was obtuse. So either one reflection or the other one does what we want. Either the sum or minus sum is also a root, so the sum is also a root. And this contradicts maximality. But beta was maximal. Okay. So this can't happen. We said.
Because the difference between alpha 2 prime plus beta and beta is alpha 2 prime, and we assume that alpha 2 prime is positive.
Yes, it is definitely positive because it is from delta 2, which is a part of delta. Yes, so this is not possible. So what did we prove? We proved that if beta is maximal, then all the coefficients are strictly positive. Now the last question, why beta is unique? Why beta is unique? Suppose that some beta prime is also maximum. So the idea is the same. Let us find the scalar product. What is the scalar product? If we take beta and beta 2 prime, not 2 prime, beta and beta prime. What do we know? We know that for beta there is always such alpha 2 prime with the scalar product negative. So for beta there exists some alpha prime which is simple, such that beta and alpha 2 prime is strictly negative. Okay? Just because it is non-positive and all these scalar product cannot be zero, because otherwise beta would be in delta orthogonal. But now we know that if we decompose beta prime, it contains beta prime is okay. With this coefficient strictly positive. And if we expand the scalar product of beta and beta prime, so beta and beta prime contains a negative summand. So how can we decompose it? Beta prime is the sum of the same alphas with positive coefficients. All the coefficients for beta prime are positive because it is also maximal, and all this can be applied. Among these coefficients, there will be something with alpha 2 prime. So beta with alpha 2 prime will be negative. Beta with all the other alphas will be non-positive. So there are many summaries. Some are non-positive and one is negative. So it is negative. And now, beta prime is Не, я не хочу. Конец доказательства уже. So we continue here. Beta prime is negative. So beta minus beta prime in phi, and b prime minus beta in phi. Okay? And so one of them is in phi plus. If beta minus beta prime is in phi plus, then beta prime is not maximal. Beta prime? Yeah. Beta is beta prime with some positive root. Beta prime is not maximal. And we are done. Any questions? questions? Okay. Okay, then one more corollary. It is also more or less clear. So let phi be irreducible. And then acts, then W acts irreducibly on our vector space. Our space, which is span phi. In particular,
Well,
yes, this is the wave group. This is the wave group, which is generated by all the reflections with respect to roots. And as we have proved last time, we can generate it only with simple roots. We take only the elements of delta and only the reflections which correspond to the elements of delta, and this will be the same group.
Reducible acts irreducibly.
So it doesn't have any invariance of space. And in particular, the W orbit of any root spans our space, spans E. So, how can we prove this? We will, yes. Натянут, если мы интерпретируем орбиту какого-то вектора, какого-то корня, то линейное подпространство натянуто на все эти векторы, span это линейная оболочка. Вот. Это будет все E. Окей. So we will prove the first part, and the second will follow clearly. Suppose that E prime in E be an invariant subspace. Make it then non-zero. Invariant on W subspace. So then, since all the elements of the W are orthogonal, then take E prime, E2 prime is E prime orthogonal, and it will be also VW invariant. Now, so clearly, since our form is non-generate, we know that it is the direct sum, and we know that for each alpha from our root system, it is clear that either, so we know that each simple reflection preserves, we assume that each simple reflection preserves E prime. So then either alpha is in E prime, or since sigma alpha preserves E prime by assumption. We know that E prime is contained in the mirror of reflection P alpha. Okay, maybe this is not quite obvious.
What is P alpha?
This is H alpha. This is H alpha. Sorry. Why is it true? Since if you diagonalize sigma alpha, it has one eigenvalue minus 1, and all the eigenvalues 1 in some basis. And H alpha is the subspace generated by all these vectors. So we know that sigma alpha preserves E, preserves E prime. What is E prime here? If so E prime is a subspace which is invariant under this reflection. How can it live with respect to this basis? If it contains only these vectors, then it is in H alpha. If our so in the case when it changes something, it changes this coordinate, and so since V is in E prime, and if sigma alpha is non-trivial on V, sigma alpha V is on E, then this difference, which is proportional to alpha, also is in E prime. So V minus sigma alpha V also belongs to E prime, which is proportional to alpha. If they are not equal, so in the case when they are always equal for all vectors V, then E prime is in H alpha, and all the points are stabilized. If for some V they are not equal, then alpha is in E prime. Okay. And so now, what does it mean? In this case, it is clear that all the simple roots split alpha doesn't belong to E prime, if they belong to H alpha for all the roots, no, if they contain if H alpha contains E prime, then yes, then alpha is in E prime, and it contradicts with irreducibility. So, and phi is not irreducible. Okay, and so we are done. So E prime is empty, and the end of the proof.
Can you just repeat this argument? I got till here that either
Mhm.
alpha is in E dash or E dash is inside this H alpha.
Okay. Yes, let us take alpha, which is not in E prime. So, what is H alpha? These are all the vectors which are orthogonal to our root alpha. So if E prime is here, then we add orthogonal and we reverse the inclusion. So E prime orthogonal contains H alpha orthogonal.
Which is alpha.
This is alpha, and this is E2 prime.
Okay.
So
Yes.
okay.
Okay. And now this root system actually splits.
Yes, and
In
now
both
everything splits into two subsets, which is not true by the assumption. So now the orbit of each root is the whole, it generates the whole space E. And so we are done. Any questions? Okay. What about the future? Do we need an introductory lecture about Lie algebras without proofs? Do you want an introductory lecture without proofs? Or что?
Lecture probably.
Ну, как бы если будет без доказательств, просто на уровне рукомахательства. И план такой, план. Надо или не надо?
Скорее к вам вопрос.
Ну, я не понимаю, я посмотрела, как бы, если я буду доказывать все, то это займет лекций 6, всех выиграть. Вот. So we have two possibilities. Either we switch to reflection groups right from the next lecture, or we have one more lecture almost without proofs about Lie algebras and about how this stuff is applied to Lie algebras. And then we switch to reflection groups.
Second option.
Second option.
That is, we have a lecture on Lie algebra and how this is related. And then
Okay, how this is related? I can't give all the proofs, but
That's fine.
they could be inaccessible. So then I will I think I have 10 or 15 minutes. I will start just a little bit about some definition with the algebras. A very little bit of the algebras. So, what is an algebra? It is just a vector space with a commutator. So, it is the vector jig thing, which is commonly used for the algebras. If you don't know how to write it, you can consult some интернет. Это такая джиготическая, очень некрасивая, чтобы путаться. Okay. So what is our operation? It is the commutator. It's the Lie bracket. So it is bilinear. And also it satisfies the Jacobi identity. You remember this from the first seminar? The Jacobi identity was x, y, z plus so you asked me what is the motivation to study the root systems. So the initial motivation to study the root systems was to classify the Lie algebras. What can I say right now? First of all, that most of the good Lie algebras are matrix algebras.
Does good means A, B, C, D, and
Yes.
else is?
Yes. So I didn't give you the definition, but I want to give it right now. So what are good? Let us define what are simple Lie algebras. So first I want to comment this part. What are matrix algebras? It means that every element is in fact a matrix. So there is bijection. Each x in J correspond to a matrix. Of some size, matrix. It is a square matrix of some fixed size. So each element of G is a matrix. So that x, y equals the commutator of the corresponding matrices.
And what do we require from this map to inject or
Is
not by injecting?
not bijected. Thank you. Yes, injective.
Inclusion.
So something like faithful representation, yes.
No, I don't want to say about representation.
Okay.
I just want to say that many good Lie algebras, so all semi-simple Lie algebras, they can be realized as a subgroup in the matrix algebra. okay, so if you know something, you can define, for example, a Lie algebra of derivations. It will satisfy all this stuff, but it will be huge, maybe not semi-simple, and so this will not be true. So we are not going to classify this. So people know how to classify semi-simple Lie algebras.
Okay, is it even finite dimensional? You said take an algebra of differentiation, but is it even finite dimensional?
Yeah, it is not infinite dimensional. Okay, let us restrict ourselves to finite dimensional Lie algebras, and among them we will classify semi-simple ones. On the other hand, there are reductive Lie algebras. They also can be classified, but using other methods.
Using what?
And other methods. So what is nice and what is combinatorial, it is at the half of the semi-simple Lie algebras. So what is the definition of a semi-simple Lie algebra? First of all, it has no abelian ideals. Ideal is I such that xy always is in I. Abelian means that if we restrict this commutator on our set, it vanishes. The first example of a not semi-simple, so GL2 is not semi-simple. Why? It is because it has diagonal matrices A, 0, 0, A. So these matrices conjugate with everything. So I, it will be the ideal. So I conjugated with GL2 is 0, so it is in I. So it is indeed an ideal. And it is abelian. So, what is the other definition of semi-simple Lie algebras, which is more close to our setting?
Почему у нас группа внезапно появилась?
Как группа?
Random.
Да. Не надо не до ну вам же это GL2, not a group but an algebra. Thank you very much for your comment. It is the algebra of all 2 by 2 matrices. Also here I write GL2. Okay. It contains scalar matrices, which is an ideal, which is abelian. So this is bad for us. So the other definition of semi-simple Lie algebras is that so trace. I should explain what is this. Generating maybe it will be hard to understand what is Nx and Ny. So Nx is an operator which acts in this space by commuting with x. So we have a vector space of dimension dj. Yeah, it is hard for understanding, but do you remember from the that we've had trace x, y, and we said that it is a bilinear form on the vector space of matrices. Do you remember this?
In symmetric.
Um,
Something like.
что? Ну, следующий цикл просто был длиннее.
Ну, у нас главное было, что наоборот, если, можете поменять местами, след останется у нас по проекту.
Да. Yeah, it was magic. Yeah, thank you very much. It was magic. So, and x and y are two linear maps, so they can be thought of as matrices. Acting in a vector space of dimension Vj by commuting with x. So, at x is an operator applied to some matrix Z is x z. So, it is the commutator of x and z. It is the definition of how adder works. And now I will check that GL2 is not semi-simple in this sense. Because what if we take this kind of matrices? So they commute with everything. For this matrix, and x will be 0. And if we take trace of 0 times something, we will get 0. So in some basis of our 4-dimensional vector space, if this is one basis vector, then it multiplies by 0 with all the other basis vectors. So this form is non-degenerate. This is a bilinear form on our 4-dimensional vector space, and it is not non-generate. So it is not semi-simple in the second sense. So that's why we do not classify in our classification. GL2 doesn't appear. It is not semi-simple. And next time I will explain if this is well defined, then we are in some Euclidean space. We can think of this as of an Euclidean space. Do I have any more time? I can talk about SO2 if you want, or we can stop. Okay, if you have time, I will give you the seminar, and this will be all for this lecture. I just explained what is the semi-simple algebra, and I will sketch some more systems in the classification of the semi-simple algebra next time. Not without proof. With examples. Мы следующий раз делаем? Вы сделали 5, правильно? Да, а мы не быстрее управляем, да?
Нет.
Замечательно. Тогда вам если